The Chemistry of COVID by Pranav and Tejhasvi. We all know that medical professionals recommend washing your hands with soap for 20 seconds to prevent exposure to coronavirus. But have you ever wondered why? To start off, everything is made up of atoms. Atoms are everywhere. Atoms of each element contain a characteristic number of protons and electrons. An element is a pure substance consisting only of atoms that all have the same number of protons in their atomic nuclei. Now this is the hydrogen element. This is the atomic number, which is the number of protons and electrons that this element has. And this is the Bohr model of the hydrogen atom. It is very useful for identifying properties and characteristics of an atom. Atoms combine to form molecules. For example, hydrogen atoms bond with oxygen to make water. But how does this bonding work? For that, we can further simplify our model into the Lewis dot structure, which only shows the required information to show bonding, such as the valence electrons. One such bond is the ionic bond, which is a bonding between two ions. Ions are atoms or molecules that have a charge due to the loss or gain of a valence electron. Cations lose electrons and anions gain electrons. Ionic bonds are formed when a cation gives up its electrons to an anion. Here you see the cation sodium and the anion chloride to form an ionic bond and form sodium chloride. Another kind of bond is the covalent bond, which is when atoms share electrons and charges amongst themselves to satisfy their outer rings. Now we have molecules. One other important idea is the idea of electronegativity. Electronegativity is the measure of the tendency of an atom to attract a bonding pair of electrons. This idea can also be used to determine the type of bonding. Drawn here is an atom stealing electrons from another atom. Using electronegativity, you can identify the polarity of molecules. Polarity is the tendency to possess two oppositely charged sides. If either side had a slightly stronger charge, it would be considered polar, such as shown here. If both sides negate each other, it would be considered nonpolar, such as drawn here. If the difference in electronegativity of the atoms is greater than 0.4, we consider it polar. If it is less than 0.4, we consider it nonpolar. If there is no polar bonds, it is also considered nonpolar. We have already learned about covalent and ionic chemical bonds, which is what scientists call intramolecular forces. The root word intra means within. The forces between different molecules are called intermolecular forces, with inter meaning between. An example of an intermolecular force is dipole-to-dipole force. Dipole-to-dipole forces are attractive forces between the positive end of a polar molecule and the negative end of another polar molecule. The two poles attract each other or repel each other, causing dipole-to-dipole forces. When hydrogen is bonded with either oxygen, nitrogen, or fluorine, it is known as a hydrogen bond, which is one of the strongest intermolecular forces. While hydrogen bonds are the strongest intermolecular force, the weakest intermolecular force is dispersion forces. The London dispersion force is a temporary attractive force that results when electrons in two adjacent atoms occupy positions that make atoms temporarily form dipoles. Now to connect it back to soap and water, which are both molecules. Water is a polar molecule held together by covalent bonds. Soap is a half-polar molecule with a polar head made of oxygen and a non-polar tail made of carbon and hydrogen. The non-polar tails of soap are uncomfortable with the polar head's attraction as they are constantly being moved around. The polar head of the soap attracts water into a hydrogen bond. Micelles are essentially soap molecules arranged with the water-attracting heads on the outside and water-repelling tails on the inside. The tails are nonpolar, while the heads of the soap molecules are polar. Now let's talk about the coronavirus molecule, which consists of a nonpolar lipid bilayer with a double layer of fats with protein spikes. Within the virus cell itself, there is genetic material such as RNA and DNA. When the coronavirus particles are on our hands and we wash our hands with soap, the non-polar tails of the soap molecules scramble to find a place to be comfortable. As they do so, they insert themselves into the outer shell of the coronavirus particle. This breaks down and shatters the protective layering and leaves the weak genetic material and proteins vulnerable. The remaining soap particles form micelles around the virus debris, allowing it to be easily washed away by water. However, for soap and water to work so efficiently against the coronavirus, you need to wash your hands for at least 20 seconds. So next time you go out, remember to wash your hands, stay safe, and remember the science and chemistry behind COVID so together we can eradicate it. Thank you for listening.